right. Hopefully you did well on quiz 1. If you didn't take quiz 1 yet, pause the video, take quiz 1 before we continue with the lesson. All right, have your homework out if you would, please. Books open to page 17. You did problems 3 and 4, and you were adding, subtracting, multiplying, and dividing numbers written in scientific notation. It's important to remember that in order to add or subtract scientific notation, there's a certain condition right up front, Kendall. Got to have the same e values or the same powers of 10. In order to multiply or divide scientific notation, is that true, class? Whatever you want, right? Multiplying and dividing. But when you add or subtract in scientific notation, once you get the same e value, it just stays that same e value in the answer. For multiplication division, it doesn't matter what the e values are because you're going to mess with them. If you multiply numbers, what do you do with the e values, class? Add them. Good. If you divide numbers in scientific notation, what do you do with the e values? And remember, when you're working with signed numbers, if one of those is a negative power of 10, a negative e value, subtraction is actually adding the inverse. So keep that thought in mind as well. One other thought we had to concern ourselves with here is that our answers have to be written correctly. And multiplication and division generally mess up our answers. They generally don't come out written properly. And so we got to move the decimal and change the e values. And Audrey, there was a couple of ways we could remember how to move the decimal and how to change the e's and weirdness like that. Do you remember the corny ways, or you could just be boring about it? How do we move the decimal, change e values? How does that get related?
Up and left and down and right.
Okay, so she said it the boring way. But if the e value goes up, we move the decimal to the left, because can you believe him? He just up and left. And if we need to make the e value go down, we move the decimal to the right, because that was downright good. And however you want to remember it, it's up to you. You can be boring about it. That's fine too. So we're obviously going to have to use some of that to get matching e values or matching powers of 10 in some cases for the addition, subtraction, multiplication, division. A lot of times going to have to do that in the answer. Number 3, you were adding, and they already have the same e's, the same exponent, same powers of 10. So really, really easy there on 3a. What was your answer, Michael?
4.384e negative 4.
Good, 4.384e negative 4. How about letter B? They weren't matching e's. I told you the easiest, best way to do this is always change to which of the two e values, Audrey?
The higher one.
Whichever is bigger. So in problem B, 3b, we're going to change both of these to be
E6.
E6s, because E5, E6, we're going to go up to the E6. And then we'll subtract, and what, we're going to get a negative answer here. What are we going to get for our answer, Audrey?
Negative 3.123 E6.
Negative 3.123 E6 is correct. Great job. Letter C. Not matching e's, so we're going to change both of them to, well, change one of them so that they both say, Kendall, E3. And what do we get for the answer on 3C?
3.754 E3.
Good, 3.754 E3. Do we need to see any of those 3 worked out? How many went 3 for 3 on number 3? All right, good. Number 4, you're multiplying, dividing. So we're going to, first of all, on number 4A, we're going to start by multiplying the numbers. And initially, when you multiply them, Michael, what's your number going to be starting out?
I don't know. I worked it out in my head. Well, I wrote down the answer. I don't have to work.
Audrey, what do you get initially for our number?
21.792.
Initially 21.792, and then of course with the e values coming back to Michael, we had to
Move the decimal left.
well, but the e values. What's the e value initially on 4a?
11.
E11, right? Initially this, but then yeah, we've got to move the decimal to the left, so our final answer should be
2.1792E12.
there we go, and that is the correct final answer. Letter B. What do we get when we initially multiply here, Kendall?
11.7623.
By initial 11.76, you said 23?
Mm-hmm.
Yeah. And when we add the e's, we're getting e positive 1, because we got a negative 2 and a positive 3. But once again, we got to shift the decimal left, she up and left, or he up and left, and so we're going to have
1.17623 E2.
and there's our final answer. I can't wait till we get to talk about significant figures and not have to write so many numbers in our answer. But for now, we'll write the whole thing out there. How many good on both A and B? Good on A and B. Hey, Audrey, question. You got it?
Mm-hmm.
All right. Looking at letter C, we've got a divide, and here, probably needed the calculator to divide that because 8.54 divided by 3.20 is just obnoxious to divide if you don't. What is that going to be, Michael?
26.6875.
It should have been 2.6 right off the bat for the division. 2.66875. But what do we have to do with the e's again since it's division? Subtract them. So we're subtracting an E6, then minus the E3 ends up giving us an answer of E3. And that is our final answer, 2.66875 E3. Now letter D is going to give you a little bit of a weird answer initially when you divide. What do we initially get on our division here? Kendall?
0.68475.
Yeah, isn't that awful? But again, if you're using the calculator to do the division, not too bad. Also with the E values, we have to subtract or add the inverse. What do we get for our initial E value?
E2.
Ooh. Careful, we're subtracting them, right? So I have a -2, and then I'm subtracting a 4 or adding a -4 because we add the inverse. So we should have gotten E -6. But is this written correctly, class? No, I've got to have one digit before the decimal. So I'm going to have to move the decimal backward here to the right. And if it goes to the right, what happens to the E value? It goes down. So instead of E -6, E -7. And that's our final answer here, 6.84375 E -7. How many have those answers for C and D? Good to go? Questions at all on this? Does it make sense now? All right. Questions at all on the homework? Well, we're going to use E values again for a little bit of what we're doing today. Next big section in your notes is converting units of measure. Converting units of measure. As we work this year, there will be times where we'll need to change from one thing to another. And really all year long, there's going to be a little of this sprinkled throughout. So it's a skill we'll continue using year long. But converting units, next section in your notes. Converting units. Now there's 3 different ways that we will convert units. Okay, so letter A, if you will, under converting units, or number 1, however you keep track of it, is converting from something that's in the SI system to something else that's also in the SI system. We used to call this metric to metric, okay, back when we were in junior high. We call it SI now that we're in science, but basically we're converting units that you would think of as being metric units. The key here, first of all, step number 1 is to determine the E values of the unit you have and the unit you're converting into. For instance, if I wanted to convert from 0.14 milligrams into kilograms. Now, you might be thinking, oh, I remember King Henry died unexpectedly. The problem is, what about mega and micro and nano? And we really don't use deca, deci, and hecto much. So do you see that the old King Henry method worked great in junior high? Technically, in this problem, it could still work because both of those are on the King Henry whatever, but there's got to be a better way, right? So we're gonna base everything off of E values, both the unit you start with and the unit that you're going to. Step number 2 is to find the difference in the E values. So you determine the E values, find the difference between them, and determine if the E is going up or if the E is going down. Am I going to shift the E up or am I going to shift the E down? And based on the way that the E is going to change, you're going to move the decimal. And technically the King Henry thing was moving the decimal, right? And that's really what it's still about. But rather than going boing through King Henry, we're going to base it all on E values. So let me show you this example. Jot this down in your notes. If we have 0.14 milligrams, I want to convert it all into kilograms. We're going to start by identifying what is the E value for milligram. Class? What is milli's E value? -3. So here we've got an E -3. What about kilo? There's a reason I had you memorize these. E3, you better know these. You're going to be using them, like I say, all year long, off and on. So we've got to know these. All right, so we've determined the E values. Now we need to figure out how big of a change is it, and at the same time, we're going to determine, are we going up or down? I like to picture the y-axis. Okay, so going back to your graphing days, I picture where -3 would be, and I picture where +3 is. Is the E going up or is it going down? It's going up. From -3 to +3 is obviously going up. How far up the y-axis does the number go? 6 units. So then I'm just going to put a little up 6. Again, all of this done pretty quickly, assuming you have your E values memorized, and kind of just a mental picture of the y-axis helps me. If it doesn't help you, you do what you need to do. I just like picturing y-axis. All right, so if it's up 6, she up and left him. All right, so we're going to go to the left 6 places. 1, 2, 3, 4, 5, 6. All of these become zeros. So we get 0.00000014 kilograms. So really ugly looking answer. Now again, technically, you don't always add 6 zeros. It's just when I happen to move the decimal, all the movements were zeros. But I did want to point that out. So we determine the E values. Figure out how far apart they are, and are you going up or down? Again, I picture the y-axis, and then move the decimal according to he up and left me, or that's downright good. All right, so let's do another one. Let's suppose we have 5.36 megaseconds. Now, I will grant you, we don't use megaseconds very often. We'll normally convert to hours or even years, even in the SI. And we want to convert it into centiseconds. Megaseconds to centiseconds, just for the fun of it, okay? And so we start by determining our E values. What is the E value for mega? Class? 6. E6. And what about centi? E-2. Again, got these memorized really well, so I know the quiz is in the past for you now, but still work on them, okay? What's the E value doing? Going from a 6 to a -2. That's going down how far? 8 units. 6 and then 2 more to get down to the -2. So I'm going down 8. Well, decimal, if the E value goes down 8, the decimal moves to the right 8. 1, 2, and it still leaves 6 more zeros to fill in. So 5, 3, 6, 1, 2, 3, 4, 5, 6 additional zeros to get 536 million centiseconds. Questions on that? Start to see the process. Let's do one more together and I'll have you try some of these on your own. Let's suppose we had 430 liters. Now that's metric. It's not quite SI, but it is, metric. We'll see liters from time to time. And we want to convert that into milliliters. Well, wait a second. Liters? There's not even a prefix there. If there's no prefix, it's E0. Does that make sense? If there isn't a prefix, then there's no power of 10 either, so it's E0. What about milli? E-3. All right, what's the E doing, class? Down 3. That's downright good, so move the decimal to the right 1, 2, 3 places. And we should have 430,000 milliliters. All right, any questions on that at all? Any questions? We feel like we understand pretty well? All right, page 17, do problem 5. Again, think through the E values, up or down and how much, move the decimal. Just a little bit longer. Most students in here finishing up. And then we'll take a look at these together. We will make sure we've got these E values memorized really well by the time we're done doing these, right? So giving us continued practice with those. All right, let's take a look at our answers. Number 5, letter A, you are changing 1,560,000 seconds into megaseconds. When we move the E, what do we end up with for, or move the decimal based on our E change, what do we get for our answer, Michael?
1.56 ms.
Good, megaseconds, 1.56 megaseconds, because ms could be milliseconds. All right, letter B, 0.0054 meters, that's E0, into millimeters, ends up giving us what, Kendall?
7.8.
That's correct for letter C. How about letter B?
Oh, okay. 0.000054.
Uh-oh, milli's E0, right? Or meter is E0, what's milli? What's milli? Uh-oh. E -3. All right, so what's the E doing?
It's going down.
Down
3.
3. That's down, right, good. So you're gonna go to the right 1, 2, 3. Should have had 5.4. You just went the wrong direction. All right, but letter C, she's correct, is 7.8. When we go from seconds, E0, to microseconds, E-6. Down right, good, go to the right 6 to get 7.8. How about letter D, 0.0285 micrograms into milligrams. What did you get? Audrey?
0.0000285.
What's micro?
-6.
E -6, and then milli,
-3.
what's the E doing?
It's going up.
Up 3, she up and, oh, I'm sorry, yes, that is correct, 0.00000285 is correct. Wow, okay. Letter E, 5,200 milliseconds into seconds, you get
5.2.
5.2 seconds is correct. Again, going from an E -3 up to the E0, up and left, go 3 places left. And letter F. All right, going from 11,300 kilometers, which is a pretty long way. Right, it's further than a 5K or even a 10K. Anyone ever run a 10K? Okay, so it's further than that. And we're trying to see how many nanometers, how many billionths of meters are in that 11.3K, if you will. It's a lot. And what is the answer. Brave volunteer to read the number. Okay, I got it. Brave volunteer. A whole bunch of zeros in there. Do we know our place value out that far? Let's say a place value together, class. We got our units and stuff. Then we have thousands, millions, billions, trillions, but we need one more. Quadrillions. So it would be 11 quadrillion, 300 trillion nanometers. So that's how many zeros there ought to be in there, a whole bunch. All right, questions on letter F. All right, hopefully we don't have to do too many calculations like that. Moving forward. Questions, though, on converting these units if you're going metric to metric or within the SI. Any questions? All right. Now, it's also possible, letter B, that you'll have to convert from the metric or the SI into the English or the US customary system. It's not going to happen very often. I don't know if you remember your junior high days and you memorized kilometers to miles and yards to meters and inches to centimeters. You remember all those conversions we had to do? We're not going to do very many of those. There's really only one fact to know. So put a star next to this. You need to know that 1 meter is approximately 3.281 feet. You need to know that fact for what we're going to do. Now, yes, you could say, well, if you're going from feet to meters, that's smaller to larger, so you divide. If you're going from meters to feet, that's larger to smaller, you multiply. We're actually not going to have to worry about all that larger to smaller business. So we're going to learn a process tomorrow that takes all that thought out. It's going to be wonderful. It's going to be super easy, as long as you have this fact memorized. Okay, so memorize that fact. Now, how do you remember which way? Because sometimes students are like, wait, which one's the one, which one's... Picture a meter stick. Now picture Michael's feet. Which is bigger, meter stick or Michael's foot? Meter stick is bigger, okay? Sarcastic answer was desired there, and you're like, no, I'm going to be honest. Yeah, the meter stick's bigger. In fact, you can fit about 3 of his shoes along a meter stick, right? About 3. About 3 of his feet on a meter stick. So, again, just visualize. I think logically, I think you'll remember which way that goes. But memorize that number, 3.281 feet, and you'll be fine. The last one, of course, is what if you're staying within the U.S. customary system? We're not going to do much within this, because pretty much everything we're doing is SI, right? But, I don't know, we can go either way here, right, back or forth. But if you're staying within the U.S. customary system, there are a couple key numbers to know. And these are things the first one's something you should have learned when you were younger, and that is that a mile is 5,280 feet. That's a number that's going to come up a lot this year, because we think miles per hour, and physics thinks meters per second. So we're going to need to be able to go miles to feet, and then feet gets us to the meter. So we kind of put these two guys together to go back and forth from the miles per hour, the feet per second, just so we can see numbers we're used to and translate that into a number science is used to, or vice versa. Also along that note, well, we think miles per hour, physics thinks feet per second. I'm going to give you this number, and if you can memorize it, which it's not hard to memorize, you can bypass some steps, and that's that an hour has 3,600 seconds in it. An hour is 3,600 seconds. I think this is easy to memorize because you know 60 seconds in a minute, 60 minutes in an hour, so it's 60/60. Square the 6 and square the 0, and there's your 3,600. All right, so if you have those numbers memorized, I think you'll be good for what we're going to be doing throughout the school year. So if it's within SI, it's all about E-values. If you try to blend in a U.S. customary unit somewhere, the only one you really need to worry about this year is meters and feet. Class 1 meter is approximately 3.281 feet. And then we need to know that a mile has 5,280 feet, and an hour has 3,600 seconds. Questions on that? All right, next section in your notes. Next section in your notes. Again, it's kind of laying some groundwork for things we're going to do throughout the year here. Let's talk next about calculations with units. Calculations with units. There are some calculations this year you're not allowed to do. Other calculations, in order to do them, you got to do certain other things first. Others, just really straightforward. So a couple of rules for calculations that involve units. First of all, you can only add or subtract like quantities. You can only add or subtract like quantities. You might be thinking, oh, that sounds like algebra, only add or subtract like terms. Yeah, kind of a similar idea, I guess. What do I mean by like quantity? Well, if we were to take Kendall's height, length, right, if we laid her down, I don't know why, anyway, carry her out, 6 people. Actually, only take 4 for this. I'm thinking on Kendall. I don't hate Kendall, for the record, I don't hate Kendall. But anyway, if we're measuring Kendall's length, and we wanted to add more length to it, maybe 6-inch high heels. If she were wearing 6-inch high heels, I'd be very nice to Kendall. But anyway, nice to any woman wearing 6-inch high heels. That's just dangerous. But anyway, if she's wearing 6-inch heels, we would add a height to Kendall's height, right? Can I add mass to Kendall's height? I could add mass to Kendall's mass, right? Put on this heavy backpack, right? That's adding mass every afternoon. Adding mass to Kendall's mass. But I can't add mass to Kendall's height. You're like, well, what if you put the book bag on top of her head? It would make her shorter than she already is, so that would be mean. Number 2, I'd be adding the height of the backpack to her height, right? So you can only add quantities that are like. You can't say, man, if I have a mass of 100 kilograms, if only I had 17 more seconds. Well, that doesn't make sense, right? So you can only add quantities that are like to each other. And in order to do the addition or subtraction, you must have, that came out rough, you must have the same units. That says must have same units. It's just hard to write, apparently, for some people like me. All right, so for instance, I can add meters plus meters. That's easy enough. I can subtract kilograms minus kilograms. I cannot add kilograms plus meters. That doesn't work. But I also can't add kilograms plus grams. That won't work either. One of these would have to change. I either need to make this grams and now I'm good, or I need to make this kilograms and now I'm good. Does that make sense? All right, so they have to be the same kind of thing. Mass and length, time and mass, they don't mix, okay? If you're going to add or subtract, they got to be the same kind of units, same kind of quantities, and the same units. Questions on that before we practice them? All right, the next rule is for multiplication and division. This is where sometimes the mind gets a little bit blown. You can multiply or divide any quantities. You can multiply or divide any quantities. I could take Kendall's mass and I could multiply it by her height. I couldn't add it to her height, but I could multiply it by her. I could divide it by her. I could do all kinds of things like that. So you can multiply or divide any quantity, but you must also multiply or divide the units as well. So if I took Kendall's height and I decided to divide it by her mass, I took her meters, I could divide it by her kilograms, but I would get for my answer meter per kilogram. I'd have to divide the units by each other as well. Or if I wanted to take Michael's, I don't know, his height and multiply it by some length of time. I could do that, but I'd have to multiply at the end his meters by some seconds. For instance, if he were lying prostrate in his bed at night and a cockroach came walking along, Michael. Well, okay, it could traverse his length in a certain amount of time. That's actually how we measure speed, isn't it? Miles per hour? How many miles divided by how many hours? So we actually are already used to this idea of dividing unlike quantities, aren't we? And just dividing the units as well. So it's not quite as mind-blowing as maybe it seems at first, but there is a little caveat. If you're dividing the same type of quantities, if I'm dividing a length by another length, I'm dividing a mass by another mass, I'm multiplying time by more time. If they are the same quantity, you must have the same units as well. If you have the same quantity, you must have the same units as well. Now, you're actually already familiar with this as well. Remember when you did area stuff? You multiply a length by another length. Remember that? And that gave you square whatever it was. But remember, I would do this in geometry. You remember? Michael's like taking notes. I would say, okay, you got this many inches for the base, and you have this many feet for the height. You can't do that. You got to make them both feet or both inches before you can do the multiplication. So if they're the same type of quantity, you have to have the same units so that you'll either get whatever the unit is squared, for instance, or you may have the units that cancel. If you're dividing, matching units will cancel. If you're multiplying, matching units will become units squared. And that's true if you're multiplying or dividing the same types of quantities. Make sure they're the same units, so either you wind up with squared units or canceled away units. Take a certain amount of length, divide away a certain amount of length, and you're left with unitless answer at that point. Look, if you would, at page 10. Page 10 in your textbook now. And let's look at some of these example problems. And it says, perform, if possible, the following calculations. Can you add 300 meters to a kilometer? Well, intuitively, yes. PE teacher says, run a kilometer, and then when you finish, all right, run 300 more meters. You can do that, can't you? Okay, but in order to do the math, we have like quantities. Meters and kilometers are both lengths or distances, but they have to have the same units. So what they did was they said, we're going to take our 300 meters and we're going to change it to kilometers. We're going to take our E0 and we're going to change it to an E3 kilometers. Well, that's making my E go up 3, right? So up and left, I'm going to go to the left 3, I'm going to make this 0.3 kilometers. Plus the 1 kilometer equals 1.3 kilometers. Make sense? Or 300 meters plus, going the other way then, 1,000 meters equals 1,300 meters. Could have worked also. Look at letter B. Subtract 400 grams from 1,980 meters. I had to walk 1,980 meters to get here. Well, if we just subtract 400 grams from that, what do we get? That doesn't even make sense, does it? Because you can't add or subtract unlike quantities. Mass and length don't subtract, so you can't do it. That's the answer. Can't do it. Letter C, multiply 4 kilograms by 1.61 seconds. Can we do that? Yeah, you could always multiply or divide. You just have to do that with the units too. So notice they multiplied the 4 by the 1.61 to get 6.44, but they also multiplied the units. Notice the answer is measured in kilograms times seconds. Weird. Oh well, that's just what it is. Look at letter D. Divide 336 centimeters by 0.480 meters. Well, since they are both lengths, they have to have matching units. So notice they changed the 336 centimeters to 3.36 meters, going from an E-2 to an E0, right? And then they divided that by the 0.480 meters, and notice the meters canceled. And their answer is 7. 7 what? 7. No unit. Does that make sense, seeing the rules here kind of illustrated out in the examples? Any questions on that? All right, well, in a perfect world, I would have you do page 17, problem number 6. There are only 4 of these. Tell you what I'll do. I'll make it extra credit. Page 17, number 6. We'll make this extra credit for you. Jot that down. I'm going to give you a ½ point per correct answer. ½ point per correct answer. So you can earn up to 2 extra credit points. All right, so page 17, problem 6 is extra credit. If you don't do it, that's okay. You don't have to do it. We will start by going over this tomorrow. If you happen to already have them done and you happen to have some correct answers, you get some extra credit towards your next test. But no actual homework this evening. Have a wonderful rest of your day. When the bell rings, you'll be dismissed.